The greatest common factor, or also called the greatest common divisor, and the least common multiple are important topics in mathematics for 5th and 6th grade. They play a key role in real-life applications and in solving fraction calculations. Today, I will explain the concepts and the methods for calculating them. The two methods are prime factorization and the Euclidean algorithm. For the simplification, we will use GCF to represent the greatest common factor or divisor. Before explaining the method, I would like to review the properties of prime numbers as well as the concepts of the greatest common factor and the least common multiple. A prime number can only be divided without a remainder by 1 or itself. 0 and 1 are not prime numbers. 2 is the smallest and the only even prime number. All the other even numbers can always be divided by 2. Example of small numbers, prime numbers, are 2, 3, 5, 7, 11, 13, 17, and so on. For example, 9 is not a prime number because it is divisible by 1, 3, or 9. The greatest common factor is the largest number that can divide 2 or more numbers without leaving a remainder. This means it's a number that fits evenly into both numbers. Let's have a look at example. Let's take the number 12 and 18. We can express 12 as a product of different factors by listing its divisors. For example, 12 is 1 multiplied by 12. 12 is also 2 multiplied 6. 3 multiplied 4. Therefore, the factors of 12 are 1, 2, 3, 4, 6, and 12. In the same way, and the factors of the 18th can be seen through the expression of the multiplication. 18 is 1 multiply 18, 2 multiply 9, and 3 multiply 6. Therefore, we can get the factors of 18 are 1, 2, 3, 6, 9, and 18. When we look at the common factors of 12 and 18, we find that they are 1, 2, 3, and 6. However, the greatest common factor is 6. How do we write the greatest common factor in a mathematical way? We just use a bracket, 12, 18, bracket is equal to 6. This is a compact way to represent the greatest common factor. What's the least common multiple? The least common multiple is the smallest number that appears in the multiples of 2 or more numbers. For example, the multiples of 3 can be written as 1 multiplied 3, 2 multiplied 3, 3 multiplied 3, 4 multiplied 3, and so on. And multiplies of 5 is 1 multiplied 5, 2 multiplied 5, 3 multiplied 5, and so on. The two common multiples of 3 are 15, 30, 45, and 60, and so on. However, the least common multiple is 15, the smallest number. How do we write the least common multiple in a mathematical way? We can use square brackets. Square bracket 3 and 5 and square bracket is 15. Now, I will explain how prime factorization works for calculating the GCF and LCM. We write the two numbers side by side with two lines. The common factors is written on the left. And we always start with the smallest possible prime numbers. For example, here is 2. It's the smallest prime number common factor, prime common factor between 12 and 18. And we write the rest at the bottom. Now I will explain how prime factorization works for calculating the GCF and LCM. We write the two numbers side by side with two lines. The common prime factor is written on the left, and the quotients are written below. Always try the smallest possible prime number as the divisor first. In this case, we write 2 on the left, and the quotients 6 and 9 appear below. Since 6 and 9 have a common divisor of 3, we continue. Now the quotients become 2 and 3, which are co-prime. This means the factorization process is complete. What's GCF? The GCF is the product of the divisors. Here it is 6. How about LCM? The LCM is the products of the GCF and the remaining quotients. There is a relationship between LCM and GCF and original numbers. We can write LCM is equal to the product of the original two numbers divided by GCF. This means that once we get the GCF, the LCM follows automatically. An example of this topic appears in the kangaroo math competition. Let's take a look at later. Prime factorization works quite well when two or more numbers have many small prime factors. However, when the numbers are large and the first smallest common divisor is also large, this method becomes inefficient. For example, here, 1102 and 1363. Which one is the smallest possible prime common factor? Can you see that? In this case, the Euclid division is an excellent tool to solve this problem. We divide the large number by the smaller number and get a remainder that is always smaller than the divisor. Then we continue dividing the previous divisor by the remainder until the remainder is 0. The largest divisor is the greatest common factor we are looking for. Using this formula, we can also calculate the LCM. LCM is the product of these two numbers divided by the greatest common factor. So we just bracket 1102 and 1363, square bracket and equal to the product of them and divided by 29. You can calculate it. For a children's festival, a 120-meter long path is to be divided into sections of equal length with marker pools for competitions. 4 pools are already set up as shown in the picture. What's the smallest number of pools that must be added? The text has stated a 120-meter long path is divided into equal sections using pools. This means we need to choose a spacing between the marking pools that works for the entire path without leaving a remainder. But what spacing can be used so that 24, 30-meter and 60-meter are also divisible by this spacing? To determine the correct spacing, we need to find the greatest common factor of the numbers 24, 30, and 66. The greatest common factor is the largest number that evenly divides all 3 numbers. We can find the greatest common factor using prime factorization. We write the 3 numbers side by side, and we start with the smallest common prime divisor first. Here it is 2, and write their quotients straight below. The quotients 12, 15, and 33 are having a further common divisor of 3, Then we factorize them further until 4, 5, and 11 are coprime. Now we know that the GCF is 6. The path is 120 meters long. If we divide the path into 6 meters intervals, we calculate it's the 20 sections in total. In the image on the right, we see that 3 sections are formed with 4 poles. This means that for 20 sections, a total of 21 poles are needed. Since 4 poles are already in place, that means 16 more poles must be added. The correct answer is C.